This video we're going to be looking at rate in thermal systems, so we have some learning goals for the video, and if you wanted to you can read through those, but in general we're just going to be looking at how heat transfers through things and how we can calculate that. So our bell ringer for the lesson: heat always flows from an area of blank temperatures to an area of blank temperatures. Explain how this concept of heat movement can lead to tornadoes. So remember, heat kind of moves like pressure. So it moves to from an area of higher temperatures, or let's say warmer temperatures here, to an area of colder temperatures. All right. So explaining this, we have, think about, you see those giant clouds, or cumulonimbus clouds here. They kind of look like anvils, the storm front there. So what's happening here is this is bringing some cold air with it, a cold front, and then it's already been hot or muggy that day, so we might have this hot air throughout the day, and this is just going to kind of cut through it. And then what we have here, we have a layer of hot air down here, then the storm front came through with a layer of cold air, maybe in that cloud. Okay, so hot air wants to move to colder temperatures. So what's going to happen is that with the right conditions and condensation and stuff like that, this hot air is going to be going up, trying to bust through there. It has an updraft, right? Because we know hot air rises. So this begins to rise, and it makes the area there. It depends on the wind and such. But let's say that there is an area in the cold air which kind of breaks open. Okay, so this is kind of not exactly how it happens, but the hot air is rushing up. So what happens is that creates, when the hot air rushes up, it can kind of go in all directions. But what happens is this starts to rotate, okay, with the right conditions, because that wind is that hot air is just rushing up as fast as it can, and then that begins to create our tornado, okay? So this is a pretty basic idea. The hot air rushing up into the cold air creates a vortex and the tornado and such like that. There's a lot more involved with like condensation and dry air, but in general, you can't have a tornado without a layer of hot air and a layer of cold air, and the hot air rushing up. So quickly review rates in other systems. So let's think about what mechanical rate was, what fluid rate was, and what electrical rate was. So mechanical rate, that could be objects moving, so that's just going to be the change in distance over time. Fluid rates, remember we had flow rate, we had flow rate, which was mass flow and volume flow. So we had those two different rates where we worked with. So it's the change in volume or mass in a fluid per time. And then electrical rates, that was the amount of charge moving. Okay, so that would be where we use coulombs and time and amps. So now we're talking about thermal rates. So we have what's called heat flow rate. So rate in thermal systems is the measurement of how the heat moves, or the flow of heat. So our equation here is Q, which would be our heat flow rate. You could also, maybe you wanted to write heat flow or something like that. All right, that's going to be the change in heat, or heat energy transferred. So this is going to be an energy value over a time interval. So some units that we could be working with for heat, we could be working with joules. Like I said, it could be a value of energy. It could be calories, or it could be British thermal units, or BTU. So when we talk about like air conditioners or heating units, we use BTUs quite a bit in America. So this is the one that we're going to be looking at for our examples. All right, so make sure you write this equation down if you need to. So it's heat flow rate. Like I said, if you wanted to write H sub flow for heat flow, it makes maybe a little bit more sense. So those are two different letters. But this will be our change in calories, or our change in BTUs, or change in joules over a time value. So let's look at a problem here. Air conditioning unit capable of removing heat from a building at a rate of 15,000 BTUs an hour. If the unit runs continually for 3.5 hours, what amount of heat is removed from the building? So we have to kind of put this together. So let's say my heat flow, just go with what I said there, is equal to the change in heat over time, change in heat energy over time. So really, we have a rate. This is our rate, right? Our heat flow rate. And then in the problem, we have a rate already. That's 15,000 BTU per hour is a rate. So that's going to go on the left side of our equation. And then on the right, we don't know the change. So it says what amount of heat is removed from the building. That's what we're looking for. We don't know that. We're trying to find what amount of heat is removed. And we have 3.5 hours. So that runs for 3.5 hours. What's our change in heat? Okay, so a little bit of quick algebra here. How do we get this out of the bottom again? Multiply both sides by 3.5 hours. And that will cancel there. So 3.5 times 15,000 is going to be 52,500 BTU. So that's how much heat we pumped out of the room. So this is the British thermal unit. That's the value that we use for heat. All right, so let's try the heat flow with another one. So a similar idea here. Instead, we're actually trying to find the heat energy or the heat flow produced by the heater here. So we have a 5,000 BTU heater running continuously for 5 hours and 30 minutes. What heat energy is produced by the heater? So our equation, heat flow, is going to be equal to change in energy over time. So this is what we're looking for again. That's how much energy is created, or that's how much energy is generated or lost in a system, or heat or something like that pumped out. So this right here, 5,000 BTU heater, so that is the rating there, which is how much it can go per hour. So we have 5,000, again, BTU per hour. We're trying to find that change. And then we have 5 hours and 30 minutes. So you're going to have to put this together into one time value. So that's 5.5 hours. And then just like up above, we'll have to do a little bit of algebra. Multiply both sides by 5.5. That'll cancel out there. And we're going to get 27,500 BTUs for this problem. So that's how much heat was generated by the heater. Okay, so that equation is pretty simple using that. We just have to kind of pick out the pieces here that we're looking at. So we have a rating for the heater. All right, so we had a rating for the air conditioner up above. And then we had a time value, and we could figure out how much was generated, how much energy was generated, or how much heat was pumped in or pumped out of a room from the heater or an air conditioner. Okay, so now we're going to kind of talk about different ways we can transfer heat. So this should be review from classes you've taken before. So we're going to kind of cruise through it a little bit here. So number one way is conduction. Okay, so this would be touching. So you touch things together. And then we have convection. So this one is like convection currents. So I think of air movement up, like the tornado action that we had. And then the last one is radiation. So this would be like sunlight. Okay, so radiation would be like sunlight. We have radiation. So if you think about being outside, you'll get a sunburn for a while due to radiation. Or you've heard of people getting radiation burns or something like that, maybe from a history class or something like that. Okay, so those are the three ways we can do it, and we can actually break these three ways down into different parts, but these are the three we're going to look at here quick. So some definitions, things for you to write down. So conduction is the transfer by direct contact, which we talked about in the last slide. Convection is when heat moves, so it's heat rises. Okay, so this would be like hot liquids or cold liquids. Hot liquids, the heat's going to rise. Cold liquids, they're going to fall because it's going to have hotter particles below that would rise. You could think of helium maybe. If you have a balloon and you leave it in the car overnight and it gets cold. Okay, so this is our balloon that we start with. It gets cold, you come outside or you go in your car or something, and that balloon is going to be flat on the ground. But then you bring it back in the house and it heats up, and then it'll start to rise again. That would be an example of convection. So we can break down convection into a couple different types. So we have natural convection, and then we have forced convection. This is the one that everybody likes, because if you have an air conditioning unit in your house or some kind of a central air system, that is using forced convection. Okay, so forced convection is essentially moving heat air, hot air, with fans or machines. So we're moving hot air from a furnace, or we're pumping out air and we're pushing cold air through a house. We're pumping out the heat in the air and we're pushing cold air through a house. That would be forced convection. Natural convection, that's just going to happen when things heat up from the sun. Okay, so this would be kind of a combination of radiation, but the radiation is going to heat up the ground, and the ground is going to have the ground is going to heat up, and the hot air or hot particles are going to rise due to natural substances or due to natural occurrences. Okay, so forced convection, that's people making fans and moving air. Natural convection, that happens by the sun heating things up, and heat transfers that way. So the third way I mentioned was radiation. So here's your definition for radiation. So it's transfer of thermal energy by waves, wavelengths, through all matter or empty space. So this could actually happen with sound waves as well. We can heat things up with sound waves. That would be resulting in friction. So radiation essentially excites the particles in whatever it's getting hit by those wavelengths, and then the excited particles bounce together, which creates friction, and friction creates heat. So those are our three ways. So talking about how well things heat up or lack thereof, we have a conductor. So we talked about this in our electrical units. So a conductor is a material which energy can easily be transferred as heat. So that would be metals, and people are actually good conductors. Anything that's metal is a super good conductor. Now there are different kinds of metals that are worse than others, but the other thing that we would be looking at that goes with conductors would be an insulator. So an insulator does not transfer heat easily. So things we use as insulators would be like ceramics, we use glass, rubber, we use rubber. Wood could be considered an insulator. We don't intentionally use wood a lot because it could start on fire if something gets too hot around it. But ceramics and glass are two big ones. If you have ever looked at a power line, or if you have an electric fence, if you're a farmer or something like that, usually there's going to be like plastic or ceramic or glass that's going to be insulating some parts of your wire, so that way it doesn't rub on anything else or touch together, because that's a poor conductor. And one other thing that goes with our conductors and insulators would be thermal conductivity. So each thing is going to have, each substance could have a rating of thermal conductivity. So thermal conductivity is a measure of a material's ability to conduct heat. So metals are going to be very good conductors, so they're going to have a large thermal conductivity value. So K is what we use to represent thermal conductivity, and the greater the value, the better the conductor. All right, so metals are going to have a large value, and wood or ceramics or glass, they're poor conductors, so those are going to have lower values. And we're going to use this thermal conductivity constant, which would be K, in equations here to talk about heat transfer. Okay, so this is our equation here. So Q sub H, that's our heat flow again. If you don't like Q sub H, you can do H sub F. It doesn't matter to me. But we have our thermal conductivity constant times the area that we're working with times the change in temperature over a uniform thickness of the material over whatever uniform thickness of the material it is. That sounds stupid. Over a uniform thickness of the material that we're working with. Okay, so a lot of the times we might use this for thermal conductivity of walls, trying to find R values and stuff like that. How well does your house conduct heat, or how well does your house insulate, rather, because we don't want our house to conduct heat, we want our house to insulate. Okay, so there's your equation, Ka delta T over I, and again, here are what those represent, and we have units for those as well. So the area is going to be in square feet, square inches, square meters, square centimeters, anything that has a square exponent, and that's going to be our area. And our thermal conductivity constant is in watts per meter times Kelvin. So we're going to try to be working with Kelvin temperatures for this one. And this is just one unit. We could have conversions of this if we wanted to. Remember, watts is a unit of power or energy. Okay, so that's where the energy and heat comes into play. That's how it connects. And then the meter is going to come into play with the area of whatever we're looking at, or maybe the uniform thickness of the material. And then again, Kelvin is our temperature unit. So let's give this a shot and use it in an example. So the wall of a house, 7 meters wide and 6 meters high, is made from 0.3 meters brick with a thermal conductivity constant of 0.6 watts per meter Kelvin. The temperature on the inside of the wall is 16 degrees and the temperature on the outside of the wall is 6 degrees. Find the heat flux or heat flow rate in this scenario. All right, so our equation, Q sub F equals our thermal conductivity constant times the area times the change in temperature over our uniform thickness of the material. Okay, so we have to kind of know what each of these are in order to use the equation. So let's find our area, right? That's going to give us that value to plug in. So that's 7 meters by 6 meters, right? Length times width, or in this case it would be width times height, because our thickness is 0.3. So that's going to be 42 square meters. So that's our area. And now we can plug everything in. So heat flow is going to be equal to our constant, 0.6 watts per meter Kelvin. And then our area, which is 42 meters squared. And then our change in temperature. So we need this to be in Kelvin because we have Kelvin there. So to convert to Kelvin, remember, it's just Celsius plus 273. So let's say our initial temperature is on the inside of the wall. So which is going to be 16 degrees Celsius plus 273. So our initial temperature is going to be 289 Kelvin. And then let's say the final temperature is at the outside of the wall, which is 16 degrees Celsius. We're going to add 273 to that, which is going to get us to 279 Kelvin. All right, so we'll just do final minus initial, 279 Kelvin minus 289 Kelvin over our uniform thickness, which is 0.3 meters. All right, so if we talk a little bit about units here, we can kind of see that that's going to cancel with one of those. So we'll have 1 meter up here. And then when we get these Kelvin here, that is going to cancel with those. So this is going to be a negative 10 Kelvin, which that'll cancel with that, right? So then it's going to have watts per meter, which, well, that meter is going to cancel out with that bottom one. So in the end, we're just going to have watts for our answer here. All right, so let's multiply everything out and divide everything out, and we'll get our answer. So when we do that math there, plug everything in our calculator, we get a negative 840 watts. So that's our heat flow. Okay, so to kind of make sense of this, when you see watts, you might think of electricity. Well, really, watts is a unit of power, which is work over time. So remember, work is a joule, and time value is second. So if we're thinking about this, negative 840 watts, we're losing 840 watts or 840 joules every second, right? So that'll be 840 joules per second. So for every second that goes by, this 16 degrees or whatever, we're changing from 16 to 6 because remember those temperatures want to equalize. So we're losing 840 joules every second. So if we increase our insulators, right, so this would go down, which would mean that we would lose more or we'd lose less energy every second. So that's how we make sense of the watts being used in this problem. So we have a few more things to discuss. So we have specific heat, and then we have heat of fusion, heat of vaporization. We've talked about these things already, so they should kind of feel like review. But specific heat is how much energy it takes to raise a substance 1 calorie per gram degree Celsius, and that could be different units as well. We could throw joules in there if we wanted to, but this is in general what we're using for specific heat. So we have calories over grams and degrees Celsius, and that's a specific heat of water, so everything is compared to that. It's just 1, which is really nice. And there's our equation, if you remember that. So it's mc delta T. So C is the specific heat value, which is usually going to be a constant for whatever we're looking at. Delta T is the change in temperature, so final minus initial, and M is the object's mass, which we have down here below. So let's try a couple problems to find or use the specific heat of a substance. So for this one, a 500 gram cube of lead is heated from 25 degrees Celsius to 75 degrees Celsius. How much energy was required to heat the lead? So we're going to find Q, right? So Q equals mc delta T. The specific heat of lead is 0.129 joules per gram degree Celsius. So again, like I said, this could be calories, it could be joules, whatever we want to use for energy. So we have all the values to plug in. So we have, make sure that this works with this. So that's grams, so we can just kind of plug in everything as we see it. So 500 grams times that value for C. And then we have to do change in temperature. So our final temperature minus initial temperature. Right, so that's going to get us 50 degrees Celsius, and then we'll have to multiply these to get a value of 3,225, and that is in joules. So not too bad. So the heat transferred, or the heat required to heat it up, was 3,225 joules worth. So let's try another one here. A 25 gram metal ball is heated 200 degrees Celsius with 2,330 joules of energy. What is the specific heat of the metal? So this one, it says it's heated 200 degrees. So this is going to be the change in temperature. I heated the thing up 200 degrees more than what it was before. Okay, and then this is how much energy we used to heat it up. So that's Q. And then that's just our mass. So we're going to have to find the value for C. So let's write our equation again. mc delta T. Oops, we want a capital T. Delta T. Let's plug everything in. So 2,330 joules of energy. The mass is 25 grams. We don't know what C is. We'll have to find that. And our change in temperature is 200 degrees Celsius. So if you wanted to, you can multiply these two and then divide, but we know that if we want to move these from one side to the other, we can just divide them both out on both sides. And when we do that, we get a value for C of 0.466. And we have to make sure our units are correct, so we have joules, grams, Celsius. So joules per gram degree Celsius. That is our specific heat of this material, and we could go look up that specific heat to find exactly what the material is if we wanted to. Okay, so the last thing we're going to talk about here is a change of state, and I'll give you some equations that go with this. So we have 4 states of matter: solid, liquid, gas, and plasma, and we can go between these depending on the energy given to a system. So some other terms that go with this would be freezing point, boiling point, and triple point might be a new one. And there are some really cool videos that you can find on triple point, but it has to have the correct environment in order to get to triple point. So it has to have the right pressure, right temperature, that kind of stuff. But it can exist at a solid, liquid, and gas at the same time. Okay, so freezing point is what the temperature is to freeze something, boiling point, temperature to boil something. And then we have a couple more down here: heat of fusion and heat of vaporization, which we've worked with before. So remember, heat of fusion is how much energy it takes to melt something, and heat of vaporization is how much energy it takes to vaporize a liquid. So going with the the properties or the terminology from the last slide, we have to talk about the change in state and different types of heat, because we're talking about heat transfer and heat flow between things. So here's a little diagram. You can see we have ice water being heated by a candle. So then that ice water gets heated to 0 degrees Celsius, and then we have a phase change. We're still at 0 degrees Celsius, and then we continue heating it up till it gets to 100 degrees Celsius, and then we have a phase change. It's still 100 degrees Celsius, but then it starts to steam a little bit. So we have different types of heat that are associated with that. We have sensible heat, so that's what we can actually measure a change in heat. And then we have latent heat. So sensible heat, you can sense it, we can measure it, we can see that with a thermometer. Latent heat, we cannot. Okay, so latent heat is usually associated with phase changes. So right at the temperature where the phase changes, then that would be where latent heat is applied, and the phase changes from a solid to a liquid or a liquid to a gas. Okay, so again, that diagram, I have it down below here with a little bit more information. So we have heat being applied to that again. So we go from -10 to 0. That's sensible heat because we can measure it. We can see the change in the thermometer. Now, all this ice is going to keep at 0 degrees Celsius, but it's going to melt, and we'd have 0 degrees Celsius water. That would be considered latent heat because the temperature remained the same, but we had a change in phase. All that ice changed to water. Okay, so another example here with the latent heat will be the water getting heated to 100 degrees Celsius, and then it turns to steam. Still 100 degrees Celsius, it just starts to steam, so that is latent heat. Okay, so here are a few examples if you wanted to think of, which we just talked about between latent and sensible heat. So I'll click through the answers if you wanted to look at them later. So the last thing we have is changes of state, which go with our heat of vaporization and heat of fusion. Some really simple equations that you can look at. You can write these down. It's mass times the heat of fusion and mass times the heat of vaporization. So each material would have a specific heat required to fuse it or a specific heat required to vaporize it. So this would be given to you, and that would be in joules. All right. So these are the last things we're going to talk about. So hopefully you know a little bit more about heat transfer and changes of phase and how the rate of heat affects objects. Thanks for watching.